about linear regression. Yep, so just some quick updates. Office hours are Wednesdays, 1 to 2 p.m. in CPH 3627. I was there today. I saw some people. It was great, and I will maintain that for the rest of the term. Okay? Assignment 3 will be released at the end of today. It's created. I just haven't uploaded it yet because office hours were lively. And then it will be due on March 23rd. So you'll have about 2 weeks to do it. Okay. So we're going to dive into this. This is Chapter 7, which is the single biggest chapter of the textbook because it's a comprehensive topic. But this is kind of the linchpin of everything we're talking about. We've talked about exploratory data analysis. We've talked about correlation. We've talked about models and cleaning with messy data sets, et cetera. And now we're getting to linear regression, which who here has done a regression before? Done a linear regression? Has anyone not done a linear regression? No shame. Okay. So some of you just don't want to say that you've done regression. So it's a very common thing to have covered. But it's one of those things that you often don't cover it in enough depth, and there's a lot of subtleties to it. And as I said, it's kind of the linchpin, because from here we start to go into other models of other linear models that are basically just transformations of linear regression. And you swap out some of the assumptions for other assumptions. You swap out some of the math and diagnostics for others. But this type of analysis is extremely powerful. So much so that in R, if you've ever seen that tilde notation, like where you have an actual expression of a formula, that is a native data type to the R programming language, and it's why I like R, because the entire way that the programming language is designed is to accommodate a linear model and expressing things in that manner. And you've seen this, I think, in terms of, we've seen it a couple times before. I don't know if we've talked about facet plots, but it comes up there as well. So by the end of this lecture, you'll be able to describe multiple linear regression, conduct multiple linear regression in R, test for assumptions and diagnose problems with linear regression in R, and interpret a multiple linear regression model and write a conclusion. Same things that we always do. So let's talk about linear regression. So you are interested in predicting physical and downloaded album sales from money spent on advertising. Your boss comes in the office and asks how many albums you would sell if you spent £100,000 on advertising. How do you answer your boss? Well, you might want to do a regression model, which gives you an ability to predict a number based off of, predictor variables, right? It's a way of predicting the value of one variable from one or more other variables. Linear regression is a particular kind of regression model that describes this relationship using an equation of a straight line. So you just kind of add things together. So this is the linear regression model. You've got B0, which is your intercept, plus B1 times xi, plus epsilon of I. And that's your prediction for a given input x. So it's very simply just a line for two variables. And then epsilon, who can tell me what epsilon I is in more detail? Sorry? Residual or error, what did you say?
If everything is right, then it's the white noise.
The white noise? I wouldn't say it's white noise. It's very close. It's a random variable, yes. So can anyone clarify? So yes, it is the error. It's not the residual quite yet. We have estimates of the residual. We'll talk about those in a second. What can we tell about the epsilon of I following probability theory?
Maybe Gaussian distribution of error.
Yeah, it's a random variable and it follows a Gaussian or normal distribution. That's one of our main assumptions. Cool. So if you have the same intercept and different slopes, you've got both of them will start the same at 0, and then the slopes are different, right? So that means B1 is different depending on which line you have, right? And if you have the different intercepts and the same slope, you end up with something like this. So we all know lines. We've seen them before in various math classes and stats classes. So that's the intercept versus the slope. So we're going to start by reading in the data, which should be included in that zip file if you've downloaded it from from Learn. You read in album sales 1.dat, and we get a little bit of information about this. So there's 200 observations in 2 columns. So we take a look at what this data is, and we see that it's a Tibble, and these values look pretty reasonable, right? We might need to know exactly what the units are for them, because I think they're in thousands of dollars or thousands of pounds, but we'll have to double check. Thousands of units. Yeah, here we go. So we can then plot it. Remember, the first thing we do with any data set is we look at the data. And so often you want to do something like this. Now note that this is actually a typo. I switched y and x in this plot is slightly different, but it should be accurate. Hope so. What do we see with this data set? Remember, always look at data first. What trends do you see? Positive correlation, yes. So as we spend more on advertising, we see more record sales. Do we see anything else going on? Is this a purely straight line correlation? No. Why do we say no? The variance, yeah. What's going on with the variance?
Seems to be a little higher.
Not constant.
Higher where? So it's, yes, okay, so yeah, it's not constant, it is changing, it's getting higher. And so what we see is that the variance is small early on, and it increases there. This is known as heteroscedasticity or changing variance, right? So we have a correlation with increasing variance as sales increase. So what we can do is we can try modeling sales from advertising spent using regression. So, does anyone know the assumptions of multiple linear regression? Homoscedasticity, yeah, so we might need to look into that. Any other assumptions?
The noise is normally distributed.
Noise is normally distributed, yeah, so the error term is normally distributed. We look at the residuals for that. Any other? There's 7 of these. Linearity, yeah, so you want a linear relationship, which is one of those secrets, by the way, for the correlation. When you're looking at correlation analysis, you want to see a line. If you see a big old curve, you can calculate correlation, but that is not explaining what's going on. Again, plot your data, right? So let's go through some of these. All predictive variables must be quantitative or categorical, and the outcome variable must be quantitative, continuous, and unbounded. Normally we make unbounded as an assumption because we can't have negative record sales or negative dollars. I guess you could maybe borrow money on it or something, or lose money on something. But these are the assumptions we have. Quantitative continuous output. It's not categorical output. Non-zero variance. You have to have some variance. Actually, we're going to come back to the homoscedasticity thing because I'm not sure that's needed here. No perfect multicollinearity. So the predictor variables should not correlate highly. We'll talk about that later. Predictors are uncorrelated with external variables. So I want to make sure they're in isolation. Residuals are homoscedastic, so they're constant variance, independent and normally distributed. So they're IIDs, independent, identically distributed variables. Linearity, outcome is actually lying on a straight line. So, I lied, there's only 6. My apologies. Which of these do we meet? Any ideas? Linearity, it looks like it's linear, yeah, I'd say. It's kind of tough to tell with the variance. Non-zero variance, yep, there is variance. There are more than 2 points, yep, and they vary. Continuous and outbounded, yeah, we can predict the sales, right? Or the money that we're going to make. So those are both quantitative variables, so very easy to do a regression on it, yeah. Do we have constant variance, though? No, so that we tend to violate. So that's one thing that we should keep in mind moving forward. And then we'll talk a bit about 4 and 5. Or sorry, 4 and 3 in a second. So, yes, we do have them all being quantitative or categorical because we have quantitative input, and the outcome must be quantitative, continuous, and unbounded. The predictor variable adverts is quantitative, the outcome is quantitative, continuous, and we can consider it unbounded. Technically, you're not going to sell negative, make negative dollars, but given the ranges that we're talking about here, you can treat it as unbounded. So just remember, it's still living in math land, but that's good enough. Non-zero variance, yeah, there are dots, they are scattered, there's very clear variance. You can calculate variance if you want, but I mean, this is very clear, right? If you have all the same point, then it won't calculate it. No perfect multicollinearity. We're going to talk about this in a second. We'll talk about when we talk about multiple predictor variables. But we only have one predictor variable, so you actually can't have multicollinearity problems here. Predictors are uncorrelated with external variables. So this is one thing we have to kind of make an assumption for. It's mostly for interpretation and for the validity of the predicted values. Typically, you just assume that there aren't any external variables. If there are, then they might be predicting the outcome better, or maybe they're causal, like they predict the predictor and the outcome variable, so there's like a hidden third variable that you haven't considered. And so that's something that we can look at down the line. But typically, you just say, I'm going to assume that these are all the variables in scope, and you just want to make sure you're not missing anything in your data set. Residuals are homoscedastic, independent, and normal. We need to check these. But to check these, we're going to compute the model first. And we did see the variance issue, but we'll take a look at whether it matters once we've created the model. Linearity, yep, it looks like it's a straight line. It's not showing like a clear quadratic or like cubic relationship or something like that. But we'll check the residuals just to make sure, because that helps us tell what's going on. So I think we have enough to proceed. To do a lot of these diagnostics, we need to produce the model. So there's one thing that came up in office hours, which is typically in these types of situations, we talk about you bring in your data, you check your assumptions first, create your model, and then you analyze the results of your model. But in practice, as I'm sure you've already discovered, even doing something like correlation can be a little bit iterative. And especially when you get to regression, you can't know if you violate assumptions until you make the model. So to check the residuals, you have to produce the model. So now you're in a situation where you don't do all of your assumptions up front. You have to do some of them, or just at least plan and think, okay, these are things we're going to check later. Create your model. Then once you create your model, you can go back and check to see if it meets those. And if it doesn't, you revise your model. So a better way of thinking about this, instead of it being you're doing an analysis and you're following a strict procedure, and by the end you end up with a final result, it's more like you're debugging a program, right? You're creating a model, and then you find out there's a problem with it, so you go back and fix that problem, reconstruct your model, and then you've got a different model, and you see if that works. And if that does work, then you proceed with your analysis, right? So here's we get a little bit of a blurred line between like this waterfall method, or like the very, very classical scientific method of make your assumptions, run your tests, analyze the results, and more of this sort of interactive developing a model mindset. And when we talk about outliers and influential points, we'll talk more about that. Here's how you do regression in R. Has anyone done regression in R? That was weird. There's like 1, 2 people, then suddenly like a bunch. Who has never typed in LM in R? Great. We're going to do it today. So the linear model function, this is in the base R package. R is built around this kind of stuff, is used to compute a regression model. A formula object, which I already raved about earlier, is used to specify the relationship. Here, we're going to predict sales by adverts. So we're regressing sales as the outcome variable on adverts, the predictor variable. And so you have sales, outcome, tilde, and then all the predictor variables that you want to use. This corresponds roughly to sales is beta 0 plus beta adverts times adverts I epsilon I plus epsilon I. So the way you do this is you type album.model equals LM sales regressed on adverts, data equals album. It looks very similar to ggplot. All of it follows very similar style syntax. And we get this model. And we have estimates for our coefficients. Ta-da, we have done linear regression. Can anyone interpret this for me? Can you say the beginning of that sentence? I missed that.
Sales is equal to 134, the value of sales we are predicting is equal to 134.13 plus 0.09 times the adverts value.
Yeah, exactly. So that's beta 0, beta 1. Can anyone interpret what the beta 0 means in this? So 134.1399, what is that number? Sorry?
Intercept.
Intercept. It's the intercept, yeah, but what does that mean in real terms?
At zero advertisement, we have this amount of sales.
Okay, so that means if we don't spend any money on advertising, we would expect to make 139 or sell 140 records, right? Okay, and then adverts. Who can interpret adverts for me? Yep.
If you put $1 more on advertisement, it will increase 0.09612 sales.
That is correct, but to be very pedantic, it's not every dollar or pound or whatever.
The change.
What is the unit of the adverts?
1 unit of advertisement.
Which is, what is in monetary values? What is in pounds? 1,000 pounds, yeah. So every 1,000 pounds is it. So I don't mean to pick on you for being like a technical mistake. Absolutely, every unit of advertising, every time you put it up, that's what you increase for the outcome of this equation. But for interpreting it, it's good to keep that in mind. So what this means is, and the outcome is in thousands as well. So that means we get another 96 records every 1,000 pounds that we spend to advertising, on average, right? Cool. So you can summarize this using summary album.model, and it'll give you a bit more information. Now we have some p-values. Who can interpret this for me? Anyone? Talk to your neighbor for 30 seconds. Figure out this output, and then I'll come talk to you first. Go. Ten seconds.
The model is not because the past plus value is also less. 0.0. Yeah.
All right. So I'll start with you, and then we'll go with everyone else. How would you interpret from this?
So for residual, we measure, they are measured from the real points from the regression line.
Yeah.
So yeah, we just extract them and find the minimum and maximum of them. So we have this amount of deviation from the regression line.
Okay.
Yeah. And for coefficients, we have the estimated ones, which are, we can call them B0 and B1, which are actually the expected values of beta 0 and beta 1.
Yeah.
And the standard error also shows can show us the quotient confidence interval. For example, 1.3 plus 7.5 will become the upper bound, and then for intercept and so.
Yeah.
For P, it shows, which is very small, so the linear regression is rejected. Yeah, I think that's it.
Okay. I'm going to come back to that last thing you said in just a second, but yes, absolutely. We have, first of all, information about the residuals. What we'll see later is the residuals are your key to understanding how good this model is behaving. This makes sense, right? Because the regression line, that's what our summary is, that's what we're predicting, that's what we understand the data to be, and then the residuals are what the actual data are, right? If you have a really big minimum and a really big maximum, that's basically your idea of how much this error is. Remember, statistics is all about quantifying error for these mathematical models that you create. So this gives you a sense of the variance in a little more detail than just like the squared root, like the variance of what's going on. We have our estimates. These match up with what we had previously. So like the 0.096, if you know, it's e to the minus 2, so this lines up with the model itself already. But we get standard error, we get a t-test, which we'll talk about in more detail in 2 weeks. But you've seen these before, and it's telling us that these are significant. So I believe that you're saying that this rejected the regression. Can you elaborate on this, or maybe do you want to elaborate on that? We'll see if we can get a more precise definition of what you mean.
That means we can say that there is linear relationship between the outcome and predictors with that beta 0 of, for example, 1.3 and beta 1 of 9.6.
Very, very, very close. Not 100% correct. Yes, we do conclude that there is a linear relationship here. Can anyone more precisely say, for either of these tests, what the null hypothesis is and what the alternative is? Let's go mathematical and see if we can narrow this down. Yeah?
The coefficient is equal to 0.
Sorry?
The coefficient equal to 0, which is beta I 0.
Is that the conclusion, or is that the null hypothesis? The null hypothesis, yeah. And then this is significant, so we reject it.
Right.
So what is our conclusion for the first one, for the intercept?
And also for the advertised.
Yeah, okay, so in both of those cases, we reject the null hypothesis that these coefficients are equal to 0 in favor of the alternative hypothesis. Can anyone tell me the alternative hypothesis? It's not equal to 0, yeah, exactly. And in fact, this might be a one-sided test, so it might be greater than 0. It should probably be a two-sided test, but we don't really talk a lot about that in this class. That's fine. So, so that means that both of these values are not equal to 0, or we conclude that they are, an actual value. And so that means there is a relationship. But do we need both of those to understand that there's a linear relationship going on? No, why not?
Without the intercept also, a factor of, it's a factor of the sales variable. So without the intercept, even the intercept is 0, then the relationship exists.
Exactly. So the top one is there an intercept? So that means, does the slope start at 0, or does it start somewhere else? It starts somewhere else. And then the adverse is the one that gives that linear relationship, right? So because that exists, we know that that's there, which is a key thing to know, that these different coefficients map to different conclusions, and when we get to multiple linear regression, there's going to be more than just the two. There'll be as many as you put into the system, right? And so you kind of look at each of them independently, and that's how you can make your conclusions. Okay, any questions before we move on? I think we've done a pretty thorough job of explaining this. Oh, is that a question? It's keep on moving, Oliver? Okay. So, that was going back. So it's your turn now. In pairs or individually, I don't really care, you can create a model by predicting advertisement spending from albums sold. So this is the idea of the inverse problem, just to practice this out. Use summary to summarize it. If you finish early, try interpreting the results and write a conclusion. So we're going to regress albums. Given how many albums were sold, how many dollars do we think that, or how many pounds do we think that they spent on advertising? 5 minutes, go. We'll resume at 20 after, and I'll walk around if you have any trouble. Absolutely.
So, like, I understand what you're saying about the y-intercept. It doesn't determine linearity at all, right?
Yeah,
Because
sure.
it's just a point,
Yeah.
But so I'm just trying to interpret the data. Is this the one that tells you what the y-intercept is, and the advert is the one that tells you what the slope is?
Exactly.
Okay.
That's exactly.
Okay, I just want to make sure my understanding is
That's 100%.
why is it that the coefficient is 0 or that that's not linear?
So I've got a couple questions. I'll try and go through each of it, and then if you have to, I'll answer it. Oh, that did not resonate. All right, let's come together. First of all, was everyone able to do the regression with LM? Or who was able to do it? Many of you? Okay, great. I received several questions about the null hypotheses going on with this output. And so I want to give a bit of I think it's good to pause here and dive into a little bit of depth to kind of break this down before we build up and look at especially multiple linear regression. Okay? So, because there's confusion about, because up till now, we've only ever had a single p-value when we ran a test, right? It tells us whether the test is significant. This model has 2 tests, right? So let's walk through this a little bit. Hopefully people can see this. And then we're looking at sales and then adverts. So let's forget about the intercept and just focus on the second line here. What is the null hypothesis for the second line? Let me write an equation. Let's do to be sales I equals beta adverts times adverts. And there's some like epsilon or whatever. But we're going to forget the epsilon for now. This is our equation. And let's say beta adverts is significant. The p-value is less than, we'll do 0.05, even though it's like it's in every conceivable notion it will be significant given this data. What do we conclude from this? What is the null hypothesis? Yes? It's changing with the variable. Let's break. So yes, that's where I'm going. So you've already seen the end of this little lesson. But let's start with what is the null hypothesis mathematically?
This is equal to 0.
This is equal to 0. So H naught is beta adverts equals 0. What's our alternative?
It is not equal to 0.
It's not equal to it, yeah. Okay, so we have a p-value less than 0.05. Let's assume that 0.05 is our level of significance, because it always is. Or everyone assumes it is. Again, it's very arbitrary, but we're going to go with that. What do we do then? Sorry? We reject the null hypothesis in favor of the alternative. Well, let's look at this graphically, right? I only have one color of chalk. Okay. What would happen if H naught was true? What would the graph look like? Horizontal. What would it look like if the alternative is true? Has a slope. We'll do a positive one, could be negative, whatever. Okay? So when you reject the null hypothesis, what are we saying? There is a slope. So we're saying it's not this. And what does this mean in terms of adverts and sales? Not correlated. Yeah, they're independent. It doesn't have any impact. If you change adverts, sales remains constant, which means that there's no relationship. So when we conclude that beta, that we have the alternative hypothesis, what are we really saying?
There is a relation.
They are correlated. There is a relationship, right? So that means as adverts changes, so too does sales. And that's the power of linear regression, right? Is that we can say whether there's a relationship between two variables, and we can do this in very complex ways. Okay, but that's only the second line, okay? So let's add in something. We'll add it in here. We're gonna say this equals, we'll add it over here, plus beta 0. Okay? So that's the intercept. What's the null hypothesis? B not equal to 0. What's the alternative hypothesis? It's not equal to 0. So let's say it's significant. What does that mean for our line? Like what are the, actually, if it's equal to 0, what do we have? The line starts at 0. What if it's not significant? Or sorry, it is significant. It doesn't. It has an intercept, so it goes like that, right? Does that matter between sales and adverts? No, exactly, because you could also, it could be like this could be your line if it's horizontal, or it could be up here, right? So if the intercept is significant, it doesn't have any effect on the relationship, other than the conclusion of the final value.
So it's always that the null hypothesis always that the variable equal to 0? Is that a good starting point?
Yeah, that the coefficient is, because what we're doing is we're saying, is there a relationship or not? And that would correspond to it being 0. And then that lets us use mathematical wizardry to figure out that you can do a t-test and calculate it. Okay, so you're not seeing if the model is significant. We'll talk about that next week. You're saying that adverts is significant and the intercept is significant. 2 tests. Only one of them looks at the relationship. Any questions? Okay, great. Let's carry on. So we've done that already. So where is all of this coming from? Well, it comes from ways of calculating variance. So sums of squares. That's why we started with variance. That's why we talk about correlation, etc. So we're going to talk about sums of squares. Let's say your boss asks for a prediction of album sales. You may offer a prediction of the mean of your data set. Say, okay, you put 100,000 pounds into promoting an album. And say you're going to say the mean is 200,000. This could be considered a default model with error encapsulated by the variance or total sum of squares. We talked about mean and variance. Those are also statistical models, right? So if you say we're just going to predict that it's going to be 200,000 albums. I don't care how much you spend in advertising. It's going to be 200,000. That would be your model. You calculate the sums of squared in that way. That's variance. Okay. The problem is the mean gets the same answer regardless of your input value. That's that horizontal line. But, so if you predicted 1 pound, you'd offer the same prediction. With a regression model, you can predict the value based on the regression line, the error from the residuals, the difference between the data points and the regression line to get the residual sums of squares. So that's why it's called the sums of squares rather than the variance, is because the variance is the sums of squares for just the mean. Right? This is the simplest model you can imagine. You summarize it with just that centroid of it being the mean. So now, instead of it being the mean, you're looking at the sums of squared versus the regression line. Those are your residuals. So you create the blue model. You look at the difference there. That's the error that you have with that model. So remember, all models are wrong, but some models are useful. You'll hear me say this all the time. You already have. We may want to quantify the improvement of the regression model over the default model, or the mean. So what we can do is we can calculate the model sums of squares from the difference between the total sum of squares and the residual sum of squares. So what you do is you calculate the variance. Let's see if I can zoom in. No, OK. So what you can do is you calculate the mean. That's your default. If the regression model was terrible, or you didn't want to do a regression model, you just say the mean, and that is an estimate of how much you would sell. You can make a better estimate, you hope, by doing the regression model. And by subtracting them, you look at this is the extra bit of variance that your model is explaining. Okay? So you're able to improve upon the mean by giving a regression.
Do you always just start with mean?
Yeah, because it's like the default option, yeah. For these kinds of calculations, that's how we've built up the theory for these sums of squares.
Okay.
So in other words, there's a total amount of variance. That's what you have with the mean. That's our starting point. And everything we do when we create our model is trying to get better than just that default average, right? Because a random number is going to be the worst. Like, that's going to be probably worse than the mean. So you have a total amount of variance in the data. You calculate this from differences with the mean. And our goal is to improve, explain some of that variance, and then the rest is error in the system, right? So it's all about how many sums of squares, or how many sums of squares, doesn't matter how many. How much variance can we explain versus how much is left unexplained? And then the ratio of those ends up being a ANOVA test, which we'll talk about later, because sometimes you might explain more from a certain model, and that can be worthwhile or not worthwhile. So you can define a measure of fit. So this is our R squared, which is the ratio of SSM, so sums of squared model, how much variance the model explains over the total amount of variance that exists. And we test if that's significant. This is an F test, because the sums of squared correlation follows a chi-square distribution, and the ratio becomes an F test, and that's and it's an F distribution. And this is the mean squared error, so you divide by the degrees of freedom. We'll talk about that in a second. Okay? So to recap, total variability, this is basically the variance. It's the scores between the mean, that's your total amount of variance in the system. The residual is the difference between what's in the data and your model. And the model is the model variability. That's the difference between the model and the mean, the amount that you have explained. And R squared is the percentage of variance that you've explained. So if the total amount of variance is a certain amount, and then you've got the sum squared model is a certain amount, then that's the proportion of variance that you've actually explained. So if we go back to our model summary, can anyone tell me the R squared that we have? How much variance have we explained? 0.3346. So 33%, a third of the variance is explained by this model. That's okay. Could be better, but could be worse. Because that's an effect size, right? So that's kind of the amount that we've explained. So both the intercept and adverts are significantly different from 0. We've concluded that. The R squared is 0.336, meaning that 33.46 of the variance is explained. We'll discuss partial R squared later. But it's similar, which we wouldn't be surprised by. Okay. Any questions there? Yeah. Can you project, please?
You want to explain the sum of squares of the core of the model and like the R squared value, what actually the ratio means and
What the ratio means?
yeah.
Okay. Shall I walk through what I just showed on the slides on Blackboard? Would that help people? Is that people, like, are people wondering what the sum squared model versus total is?
Like can you please explain like to run a graph and what actually from what is what the difference is?
Okay, yeah. Let's get graphical here. So we'll go over here and give people on this side a little bit of a break. So let's say you have a regression model. We've got our sales, and then we have our advertising pounds. And let's for simplicity just go from 0, it doesn't really matter. You've got some sort of line and you've got your data, right? Okay? And if you calculate the mean, what would it look like? It'd be like kind of like this, right? So the variance in this data, how do we calculate the variance? Sorry? Sums of square, yeah. So you take the mean. I'll do M. And then this is the variance right here, right? You take all these values and you sum them up, and that's the variance that we have. That is, the data will always vary, right? You've got different data points, they have different values, and so the variance is just like something we know how to calculate. It tells you just how much difference or how much variability there is, right? And we base off the simplest possible model we can think of, which is the mean. Okay, so that's the total sums of squares. can do better than the mean. It looks like there's a relationship here. So if we want to predict sales, we'll actually make it dependent on adverbs. So we create our regression model using lots of fancy linear algebra. And now we have different error, right? So I wish I had different values. So this is the error right here, right? Because this doesn't describe it perfectly. Now, these dotted lines are the error we have with our new system, right? Oh, there's another one right here. Which is better, the mean or the line? The line. How do you know that? The error is less, yeah. So these guys, the dotted lines, this one's pretty big, but the rest of them are quite a bit smaller. Whereas if you sum the square of all these, the value is going to be quite big. What that means is you've got, like, this value is what you're explaining. So we can't explain that. So we create our model. There's a certain amount that's completely unexplained. So that's our error. But there's a lot that is explained, right? So like this is sort of like the improvements, like the difference between these two, right? So this is where you get the model. So the dotted lines here. Dotted line is error. Solid line is total. And then the curly brace is the model. Because that's the difference between the model and the mean, right? So the improvement is like this to that is the improvement, right? And this is the kind of the total variability from the model. This is not much of an improvement because this is just close to the mean. But yeah, this to this is the improvement. This to this is the improvement. So from the solid line to the dotted line is the improvement, right? And so what ends up being is, of your total variability, you kind of subtract the difference between two. This is your model, and this is your error. So of all the variance, of all the variability in the data, we explain some proportion of it with the model, and we get rid of that error. What would happen if we had a line that went like this? Let's go. If we were able to produce that curly line, what would happen to our model? Sorry? Error is 0. So what's our model? Explains everything, right? So has anyone seen stuff like that before? Those of you who are geeking about machine learning? Well, it's overfit. Yeah, exactly. So, and the reason it's overfit is because if you get more data, it might be here, it might be here, it might be here, right? And so that difference is going to be quite big. So it's not robust to new data, right? So you want to prevent that kind of overfitting, and we'll talk about that when we talk about model selection. But so one sec. So the whole point is there's variance in the system because your data vary a certain way. You try and explain it using some model. Whatever's left over is your error, and then the ratio of the percentage that you've explained is your sums of squared model. It's like your R squared. It just says here's how much variance that you explained. Yeah.
So is that 33% the improvement that the new linear model made above the mean model?
Yeah.
Okay.
Yeah, exactly. Because the mean model is just how we calculate the variability to begin with.
Yeah.
Yeah, because we need to calculate variance somehow. What other questions do you have? Okay, cool. I hope those of you who are interested in machine learning are satisfied that we dip into those topics occasionally. It is related. Okay, so using the model, if you want to provide confidence intervals for the coefficients, you can use conf_int. It's useful for testing if they're different from 0. And so you can actually get a 95% confidence interval of these values. And so what you can do if you're calculating So you've got intercept and adverts. Again, you have a t-test, right? Which means they can also just calculate a confidence interval. And so if you're talking about that relationship, you can put quantified error on explaining whether if you give no dollars, what the range would be. And so if you spent nothing on advertising, you would expect you'd sell about 120 to 150,000 units. And as you increase for every 1,000 pounds that you spend, you go between 77 to 115 new units sold.
There is no assumption of normality in this case?
There is. We're going to get to that. Okay. The assumption of normality. Can anyone tell me what the assumption of normality is going on here? So we need to make sure that works before we can do this. Okay, we'll talk about it in a second. So you can also graph the plot with ggpredict. That's a pretty convenient little thing. And this gives you this confidence intervals too for the mean. So if you're predicting the average number of sales, it'll give you that bound. And as you see, it expands as you have fewer data points. Okay. To use the model, you can calculate the predicted values manually using the coefficients. So you can use that little $sign to access that. You can save it as a variable, as we've done before. So to predict the sales from 100,000 pounds, which is our original goal, you calculate 134.1399 plus 1.096 times 100,000. So you'd expect 9.61 million albums sold. Not too shabby. One way to do this is with predict LM. So you can create a bunch of values. So this is just, you create a predictor value. So this is to predict everything but from, let's say you want to put 1 pound in and you want to put a million pounds in. You give those two values and then you can predict that, if you put 1 pound in, you're going to sell 134 units, or 134,000 units. And if you put a million pounds in, you're going to sell 96 million units. Now, if you look at those extreme values, you're probably going to, the fact that this is a linear line, a line that's unbounded, it's probably going to be, at those extremes, you might get like a sigmoid function. So, you want to not trust things outside of your data set. That's extrapolation. Extrapolation is very noisy. Okay. So what we're going to do, we're almost at 4. Okay. We'll finish this slide set and then we'll take a break. So we'll take a 5-minute break to do this, your turn. So predict the sales for advertising budgets of 10,000, 50,000, and 200,000. So write up a short conclusion. Make sure you include units. Again, the idea that it's in thousands of units is important when it comes to interpreting it. If you're done early, write up a more general conclusion. As album sales increase by N pounds, how should sales increase? And include a 95% confidence interval, saying that if you add an extra 100,000 pounds, you expect the minimum value to be this and the highest value to be that. Okay? So 5 minutes. We'll come back together at 10:02. We'll talk about assumptions, and then we'll have our official full break in this session. Okay? Go. it. So a value of 0.096, right? So every time you increase that slope is as you go up 1,000 pounds, you start to sell at 96. So that is compensated, right? That value, the beta 1, or beta adverse in this case, is between 0.77 and 0.115. So how would that be?
Okay, so we can discount with the lower bound of it.
Of the actual goal, yeah.
Okay.
So what I'm intending here is saying, like, as you spend like 1,000 pounds,
Oh, your error grows.
yeah, you expect to sell between 77 and 100. That kind of thing. You get comfortable on the coefficients, which gives you comfortable with the slope. You interpret that by saying, like, oh yeah, if you're going to spend, for every dollar you put in, every time you put in, 1,000 pounds put in, this is how many more dollars you get.
Okay. Is there a way to do it or just put in like automatically maybe two equations?
I think it's maybe
Okay.
R will calculate for you.
Yeah.
But I think that's it. I don't know about sharing the way to do that part.
Okay. All right. Thank you.
The second part, you mean? Yeah, so the coefficient of the slope, beta average, is 2196. So what that means is every time you spend 1,000 pounds, you try to sell 96. So that has gone to 0.077, 0.115. Right? So what that means is every time you quantify that, so every time you spend 1,000 pounds, you expect to increase the so 96. But probably you have 99% chance, 95% chance would be 77. That gives the variability of the that would, yeah, it's yeah, it's much more than the slope. The slope is constant, right? I'm saying that the slope should be a little bit more than that. That's sort of like saying. Yeah. I know this is it was the axis that you're putting in your calculator. Yes, I feel that's it. Yeah, yeah, which is not that would be 1. I guess that'd be 1,000. 1,000. When it comes up is 1, 2, 8. Even though this shows the interception. Yeah, exactly. So, yeah, not terribly exciting for a All right. Let's come together. We're going to talk about assumptions real quick, and then we're going to take a nice long break. Yep. So, okay, so before we can make a final conclusion, so we've been doing a lot of this analysis assuming our model is correct, right? But we don't actually know yet, because we couldn't check all of our assumptions beforehand, because some of them depend on the model. Specifically, they depend on the residuals. So, diagnosing problems with regression. You can access residuals with the residuals value from an LM object. So if you create album model, you give the $, then type in residuals, you get the residuals for every data point. This tells you the difference between the predicted value and the actual value, right? Or sorry, the other way around, I think. The actual value minus predicted. Yeah. So what you do is you can do some tests. First, you can test for independence. The Durbin-Watson test tests for independence of residuals. So it checks for autocorrelation between residuals. And so I'll show you what this looks like. DWT equals Durbin-Watson test. Give the outcome. And this is slightly different from the slides that I posted, but it's the same kind of outcome. And we see that the lag of 1. So what this is doing is it's seeing if, basically it's checking for a time series. If your data is like the stock market or whatever, a regression model is going to be bad because every stock value depends on the previous value. And so what the Durbin-Watson test checks is there a correlation between every value and the previous value? And if there is a correlation between those two values, you probably have a time series, and you shouldn't be doing linear regression. You should be doing a different model, okay? Because that means they're dependent. There are other dependents that matter, right? But what independent samples typically means is like you have a random sample and everything has no knowledge of the other sample points, okay? So here we run this. We have an autocorrelation of -0.04. That's a pretty low correlation. We're going to do a test with the DW statistic to see if it's equal to 0. P-value is 0.836. So can anyone guess what this means? It's not significant. And I believe the null hypothesis is that it has an autocorrelation, or sorry, that there's no autocorrelation, and that autocorrelation is equal to 0. We fail to reject that null hypothesis, so we can continue with the assumption of independence, okay? So the Durbin-Watson test for independent errors was not significant at the 5% level of significance. You give the D value and the P value. As D is very close to 2, which indicates no autocorrelation detected, we do not reject the null hypothesis that the errors are independent and continue with the assumption of independence met. So again, you want to be very careful with time series. This checks for that. Plotting residuals. The base plot function is good for getting.
Significance of D being 2?
So that means that
That's a computer.
it's sort of, it means that there's no autocorrelation is what it really means. I think it's expected. I think if there's absolutely no auto, if it's complete random noise, absolutely zero relationship found, it would, the DW statistic would equal 2, and then the p-value would probably be 1. I think. I don't know a ton about this test, but I usually just look at the p-value. Okay. Base plot's good for getting a series of diagnostics plots. So the convenient way to look at this is just to type plot album model, and you get a bunch of these plots. So I'm going to see if I can zoom in a bit. So first of all, we get residuals versus fitted. So we're plotting the residuals over time. What does that tell us? Can anyone tell me? Sorry?
The variance is
Variance is decreasing, so you might have a problem with variance. What else does it tell you?
linear.
It's linear, yeah. So what we're doing is we're plotting the residuals over the course of the model. We see that the variance decreases. That's that could be a problem. We're going to talk about that in a bit. But we also see that it's not, there's no like shape to it. So that means the residuals follow the line, and so we have the assumption of linearity, which is good. Below you see a QQ plot. We know and love that plot. What do you see for that? It's normally distributed. That looks pretty normal to me. A little bit of roll off on either of the extreme values, but you know that happens. We'll talk about that a bit more in a second. But yeah, so that's good. So it looks like we have some normal stuff. So the first plot is good for diagnosing residual assumptions, homoscedasticity and linearity. We probably don't have homoscedasticity, but we do have linearity. Second one is good for, yeah, so these are some examples of how these plots might turn out, right? What do we see in the first one? We see linearity. What else do we see?
Variance.
Sorry?
Variance is high.
Variance is high. So high variance, but what's the more important thing about it? What's happening with the variance?
It's uniform.
It's uniform, constant. What's the magic word? Homoscedastic. Yes. Homo being same, scedastic being variance. So, so you've got homoscedasticity and linearity here. And the second one, what do you see?
It also has variance, but it's not uniform. It's not homoscedastic.
It's not homoscedastic, yeah. So it's heteroscedastic. Hetero being different, right? But is it linear? What do people think? I'd argue that the second one up here, sorry, this one right here, is linear, right? Because it kind of follows the line, but it's not homoscedastic, it's heteroscedastic. Bottom left, what do you see? It's nonlinear. How's the variance though? It's uniform, it's homoscedastic, yeah. And then finally, what's the last one give you? Nonlinear and heteroscedastic. There will be one of these on the final exam, so you have to be able to identify which of them it matches, okay? But you see you can diagnose both of these problems. This is a quadrant that gives you all, like, examples of all 4 arrangements. And you should know the QQ. Third and fourth, we'll talk about next class when we talk about outliers and influential points. So we're going to take a full break now. You can plot the diagnostic plots and give an analysis for that during the break. And the key thing to think about these assumptions is that the conclusions aren't general. So the model we produce will describe the collected data, but if the residuals aren't normal, then it can't vary, right? Like we can't say, in general, album sales will match this certain thing. So that's kind of the important thing, is that this will still be the best fit line given the data that you have. And so if you want to estimate just in that closed system, but if you want to reach a general conclusion, you really have to give caveats and say, look, we don't really know, we don't meet the assumptions. So there might be something else affecting our data, maybe another variable too that we haven't considered. That might help address this. And that means we should go look at multiple predictor variables, which we'll do after the break. So key takeaways. Linear regression is a common technique for predicting an outcome variable from predictors. The model has several assumptions that need to be checked, often after creating the model. Coefficients can lead to interpretable and actionable results if assumptions are met. Sums of squares are a very general way of breaking down variance for statistical models. R squared, you've seen before, you'll see it again. It's the amount of variance explained by a model. And you've seen this in correlation, where R squared is R squared. Little r is big R, right? In this case. Comparing how much each model or variable explains the variance will help us pick the right model and discuss relationships between the variables. We'll talk about selecting your model next week. So, be able to run, interpret, and check assumptions of linear regression. We're going to take a 15-minute break, and at 4:15, we will come back together for the second half of the class. Get up, stretch, go to the washroom, get some water, whatever you need to do, take care of yourselves.